So in the previous video, we looked at the concept of perceptron. In perceptron, we do take the weighted sum of the inputs with the weights W0, W1, W2 and Wn, and then we apply non-linear activation function to get the Y prime. In this video, we'll be looking at the concept of deep neural networks and the loss function. So first, I will be representing the perceptron in much more compact notation. So I'll be representing the perceptron with a single node or a single circle over here. So what Z represents over here, Z is the weighted sum of x1, x2 and xn up to xn. So you can see Z is W0 plus summation over xj wj, where j is ranging from 1 to n. And then we apply a non-linear activation function on Z to get the final output, which is y. Few observations over here. Here we did had the n-dimensional input, which was x1 to xn, and we were getting a scalar output which was a single value, which could be any float over here, any float value over here. Now let us consider the case where we do have two perceptron instead of a one perceptron. In this case, again the input is same, which is n-dimensional input, but the output we are getting is a vector output. We'll be getting two outputs, y1 and y2. The y1 is, so at perceptron 1 we'll be getting the value z1, at perceptron 2 we'll be getting the value z2, and y1 is nothing else but the activation function applied on z1, and y2 is activation function applied on z2. So the weights that are associated with the perceptron 1 are W01, W11 and Wn1. So Z1 will be the weighted sum of our input with this weights W01, W11 up to Wn. So you can see this is the equation for calculating Z1, which is W01 plus summation over xj wj1, where j is ranging from 1 to n. So this is how we calculate Z1. Again, for the perceptron 2, the weights associated are W02, W12, Wn2. So you can observe over here the second index that we are having. This represents the number of neuron over here, or the number of the perceptron over here. So because we are at the second perceptron, that's why the second index is 2 over here. Now we'll be taking the weighted sum of our input with this weights to get the Z2, which is the value at our second perceptron. So Z2 is equals to W02 plus summation over xj wj2, where j is ranging from 1 to n. And then we'll be applying a non-linear activation function to get the output y2. Now let us consider the case of multiple layers of or single hidden layer neural network. So here we do have two layers of perceptron, layer 1 and layer 2. In layer 1 we do have 4 perceptron or 4 neurons. In layer 2 we do have just 2 neurons in this case. In the language of artificial neural network, the very first layer where we do have the input is called as the input layer. The final layer where we do have the final output, this is called as the output layer, and everything which is intermediate, which is between input layer and output layer, is called as the hidden layer. So in this case, I do have just a single hidden layer. That's why this is called a single hidden layer neural network. The weights associated with the layer 1 are W1, and the weights associated with the layer 2 are W superscript 2. So the value in the superscript denotes the layer of our neural network. Since we are in the first layer here, that's why superscript is 1. We are in the second layer over here, that's why we have the superscript 2 over here. Now let us see how we can do the calculation for Z2 over here. So the weights associated with the Z2 are W112, W122, W1N2. So this 1 in the superscript again represents the layer. So since Z2, this particular node is in the layer 1, that's why in superscript we do have 1, and in the subscript we do have 1, 2, where 1 represents the first input, 2 represents the second input, and n represents the nth input. So we can see what is Z2 over here. The equation for Z2 is W02 with superscript 1 plus summation over xj wj2 1, where j is running from 1 to n. Now the output of our perceptron 2 in layer 1 is GZ2, where we have applied the activation function, non-linear activation function on Z2. So this output of our second perceptron will get into the neurons of our neurons in the second layer. So you can see for this neuron which is in the second layer, the first neuron in the second layer, the input for it are GZ1, GZ2, GZ3 and GZ4. So in the similar way as we had the input for our first layer, the input for the first layer were X1, X2 and Xn. Similarly for the second layer, the input will be the output of previous layer. So the output of this layer is GZ1, GZ2, GZ3 and GZ4. This will be the input for our second layer of the neural network. Okay, so if we have just one layer of hidden layer, then we call it as a single layer neural network. Let's say if we have 10 layers of hidden layers, 10 hidden layers, then we'll be calling our neural network as a 10 layer neural network. Okay, in general, we can have n hidden layers, and since we are having n hidden layers, there are many hidden layers in our neural network. We call such neural networks as a deep neural network. Okay, so now we'll be starting with one example. I'm taking the same example as I took in the previous video. We want to predict whether the student will pass the exam or not. We do have two features over here, x1 and x2. The x1 is the number of hours a student is dedicating in self-study, and x2 is the percentages of his attendance. So x1 is 2 over here and x2 is 90. Now let's say using a simple neural network architecture over here, we did predict it for this particular input that the probability of a student to pass is 0.1. The prediction that we got is 0.1. But the actual value that we have is that a student has passed the exam, that's why the value is 1. So you can see there is an error in our prediction. Our prediction would have been right if our prediction would have been closer to 1, but it is very far away from 1 and it is close to 0. So this is not a correct prediction. So what we can do is that we can do the error calculation over here. There are multiple ways to do the error calculation. One very simple error calculation is take the difference between the actual value and the prediction value. So the actual value is 1, predicted value is 0.1, so the difference is 0.9. This is one way of calculating error. Another way of calculating the error could be to take the square of this error 1. So in this case, this value will be 0.81. In this way, there could be many multiple ways to calculate the error. In general, what you need to remember is that error is a function of y prime and y. That is, error is a function of predicted value and the actual value. In general, in machine learning, we do calculated many sophisticated errors. We call those errors as a loss function. So you can see over here that loss function will again be the function of y prime and y, as was the case for the errors. Y prime is nothing else but it is a function of x and w, where x is an input and y is an weights of our neural network. So loss function is nothing else but a function of prediction and the actual value. Now let us consider a case where we do have a big data set. We can calculate the loss on individual instances. So here you can see this L is a loss calculated on individual data set, and we can take the summation over here. So for example, you can see for this instance, we got the prediction 0.2, but actual value is 1. So this particular example will be providing us certain error. So this will be the L1 over here. Then we can calculate the error due to the second prediction. This will be L2. Then we can calculate the error due to the third prediction. This will be L3. So from L1 to Ln, we can take the summation over here where I is ranging from 1 to n, and then we can take the mean of this. So this complete loss that we are calculating over here, we call this as an objective function, and or we can also call this as a cost function. So here we have actually calculated the loss for the complete batch or complete data set. Now you can see over here that objective function or cost function is again the function of w, where w is the weights of our neural network. For binary classification problem, the loss that we calculate in general is called as the binary cross entropy loss. So the formula for calculating the binary cross entropy loss for a single instance or single example is this, where yi is the actual value of our ith instance and fxi, this value, this is the prediction that we have done, and this is the formula for calculating the loss for the ith instance. And then we can take the mean of this li or I ranging from 1 to n to get this cost function or objective function, which is j of w. So the thing that you need to remember from this slide is that for binary classification problem, the loss that we calculate is called the binary cross entropy loss. Similarly, for regression problem, in regression what we do actually is that instead of predicting the class that a particular instance belongs to, so in the case of classification we were calculating whether the instance belongs to class 0 or class 1, but in case of regression we do try to predict the continuous value. So here you can see I have predicted over here the values like 60, 20 and 44, but actual values are like 63, 40 and 38. So this represents the final grade of the student in this particular example, you can see. So initially we were trying to predict whether the student will pass or not. In regression problem, instead we are trying to predict what will be the final grade of the student. Okay, so in this case the loss that we calculate is called the mean square error loss, which is the, so first what we are doing is that we are just calculating the difference between the actual and the predicted value. Then we are calculating the square of that, and then we are taking out the mean of it over the whole data set. So this gives us the final objective function j of w, which is the mean square loss over here. Okay, so this is for this video. In next video we'll be seeing how we can use this loss function that we have calculated over here to optimize the weights of the neural network. Thank you so much.